I now call to order the Society's 2,401st meeting in the 148th year since its founding in 1871. Good evening, everyone. Good evening. As most of you seem to know, my name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Lee Cronin in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW's YouTube channel. Tonight we honor the Society's presidents, including founders Joseph Henry, John Wesley Powell, Asaph Hall, Spencer Fullerton Baird, Montgomery Meigs, Salmon Chase, and Simon Newcomb, to name a few. In accordance with PSW tradition, I will be using the historic gavel of the Society, made from the timbers used to rebuild the White House in 1816 and recovered during President Coolidge's renovation of the building in 1927. I think we are well advised to recall that the Capitol was burnt down by those of the special relationship
I'm sorry.
of the United Kingdom. Unfortunately, bygones are bygones. And tonight we're very happy to have an Englishman speaking who is living in Scotland, who comes often to America. We'll begin with a few announcements, a reading of the minutes of the 2,400th meeting, and the lecture by Dawn Tilbury on NSF's 10 Big Ideas. We'll then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. But first, please join me in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous anonymous donor. Also, please join me in thanking the sponsor of tonight's lecture, the law firm of Mill & White, Solano and Brannigan, where, in the interests of full disclosure, I have to say I am a director. So I'll thank myself. I am pleased to announce that the following new members have been elected to society, some of whom are with us tonight. First, Maribel Martinez, a new student member inspired to join PSW by a lecture she attended on black holes. And she's interested in biology, especially microbiology. Noah Leslie, an analyst with Bloomberg, interested in biology and data science, who learned of PSW through a friend. Camille Lance, a space industry consultant with Regius Space, interested in theoretical physics especially, who joined PSW on the recommendation of her boss. If you're looking for a job, I suggest that you speak with her because he sounds like a good boss. George Elliott retired from the senior executive service at the USPTO after a notable career advising on patents, patent law, and innovation policy, interested in the biomedical sciences and in innovation policy, who comes to PSW through friends at the University of California, San Diego. Stephen Peterson, a cybersecurity engineer with the Department of Defense, interested in cryptography and mathematics, among other things, who comes to PSW through Meetup. Greg Edwards, a scientist with the Academy for Advanced and Strategic Studies with wide-ranging interest in sciences, who comes to PSW through a friend. Richard North, a former PSW speaker and returning member, is a retired neurosurgeon and presently president of the Neuromodulation Foundation. And tonight's speaker, Lee Cronin. who has rather wide interests in science, as he will tell you about tonight, and whose background and interests will become more clear to you in part from tonight's proceedings. Please join me in welcoming them to the Society. All our new members can receive a signed copy of Volume 1 of the PSW Bulletin, which no doubt they will find endlessly fascinating because it describes why PSW was originally called the Philosophical Society of Washington, who were the original founders, what their purpose was, and the first 50 meetings, what they actually said. So if you are a new member and you haven't got your copy of Volume 1 of the PSW Bulletin, please see me after the lecture and I will give you one. Now, Recording Secretary James Heelan will read the minutes of the 2400th meeting and the lecture by Dawn Tilbury on NSF's 10 Big Ideas that was delivered here at the Cosmos Club on December 7th of last year. James.
Thank you, Larry. Good evening, everyone. On December 7th, 2018, President Larry Milstein called the 2400th meeting of the Society to order at 8:04 p.m. here in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Dawn Tilbury, Assistant Director for the Directorate for Engineering at the National Science Foundation, or NSF. Her lecture was titled NSF's 10 Big Ideas, Advancing the Frontiers of Science and Engineering. NSF is broadly tasked with promoting the progress of science to, quote, advance the national health, prosperity, and welfare, and, quote, to secure the national defense. In fiscal year 2017, in pursuit of its mission, NSF spent 93% of its $7.5 billion budget to other organizations to fund research, education, and related activities. In that context, NSF has developed its 10 big ideas for future investments that it believes are ripe for rapid advancements in science and engineering that will have significant societal impacts. Tilbury began by emphasizing NSF's 4 process ideas, which she says are fundamental to the success of the 6 research ideas. The first process idea is growing convergence research at NSF to fund high-risk research requiring collaborations between disciplines. Last year, NSF received more than 100 proposals for convergence research, including those to address food, energy, and water concerns, pandemics and infections, and disaster preparedness and recovery. Second is to establish a method for funding mid-scale research infrastructure in the $7 to $70 million range. NSF has already received more than 200 responses for research ideas and is now soliciting project proposals. Third, solicit the general public for more big ideas via the NSF 2026 Idea Machine. Open from August 2017 through October 2018, the Idea Machine received over 700 submissions. NSF will evaluate and select several dozen submissions based on the potential value to society. Selectees will be invited to make video presentations for public comment. Ultimately, NSF will fund finalists up to $26,000. And fourth, NSF includes to expand participation in science and engineering to all sectors of society. To illustrate the need for such effort, Tilbury described both the systemic obstructions she encountered in her own engineering career and more research conclusions recently released on continued obstacles for members of underrepresented communities in science. Tilbury then briefly addressed each of NSF's 6 research ideas: Windows on the Universe, Multi-Messenger Astrophysics, Navigating the New Arctic, Understanding the Rules of Life, The Quantum Leap, Leading the Next Quantum Revolution, Harnessing the Data Revolution, and The World of Work is Changing. Tilbury concluded by discussing convergence accelerators, components of a strategy to encourage multidisciplinary collaboration that NSF hopes will lead research to progress more quickly than if conducted in isolation. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:42 p.m., President Milstein adjourned the 2,400th meeting of the Society to the social hour. Temperature, 1 degree Celsius. Weather, mostly clear. Attendance in the Powell Auditorium, 100, and viewing through the live stream on the PSW Science YouTube channel, 24. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Do we have any corrections or comments on the minutes? If not, I'll entertain a motion from a member to accept the minutes as read. Second, all members in favor? All members opposed? The minutes are accepted as read and will be posted to the website in due course. We now turn to tonight's lecture on personalized drugs on demand, the digitization of chemistry, and it is my pleasure to introduce tonight's speaker, Lee Cronin. Lee is Regius Professor of Chemistry in the School of Chemistry at the University of Glasgow in Scotland, where he was previously Gardner Professor of Chemistry. He is also visiting professor at Beijing University and is currently involved in more than 150 collaborations throughout the world. He just told me he traveled 400,000 miles last year. Lee's eclectic mix of research focuses include studies of electron transfer, novel chemical synthesis, the exploration of complex chemical systems, the creation of artificial, or synthetic, if you will, life, and making and using nanoscale molecular architectures. His tools are likewise interdisciplinary, and beyond the apparatus and methods of chemistry, his endeavors develop and employ specialized robotic systems, artificial intelligence, and the generation and analysis of very large data sets. Lee is an author on more than 400 scientific papers, including many cover articles in the primary scientific literature. He is also an author on 2 books, an inventor in 10 patents, probably more now, and the founder of Deep Matter, a company focused on chemical robotics. Lee gets around, speaking widely on his research, as well as maintaining his many collaborations. He's given over 400 invited lectures at last count, including the Weissman-Perlman Lecture, the Solvay Lecture at the University of Belgium, and PSW's own 81st Joseph Henry Lecture. Among other honors and awards, Lee has received the Royal Society of Chemistry's Interdisciplinary, Tilden, and Hutton Prizes, the Corday Morgan Medal and Prize, and the Royal Society's Wolfson Award. He earned a BS and PhD in chemistry at the University of York. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Lee to the podium.
I think it works. Thanks, Larry.
Just need to bring it up.
Okay. Thank you very much, Larry. Cheers. So, good evening. It's a pleasure to be here. I'll try not to walk around too much and stuff out my... I am a chemist, but I kind of realized, and I was talking to someone earlier this evening, a very young person come here, that trying to explain that although I do chemistry, I'm interested and always wanted to do science. I never really understood what that is. And what I'll tell you a bit about tonight is something that's fairly utilitarian, but actually is leading to really interesting science. The reason behind all the stuff we're going to talk about in terms of this digitization of chemistry and using these robots, as it were, this kind of nice eclectic idea of this machine and this flask doing chemistry, and it's maybe this robot will replace all the chemists in the world and make them entirely redundant, is not the idea. The idea behind all of this really stems back to, and some of you actually saw the Henry lecture that I gave, which was rather naive back then, but really we're continuing to do, which is, can we make a life form that is not based on the biology that we know on Earth? And this is a really big question that allows us to kind of think beyond the chemistry that we know. Well, what I'm going to do tonight is not really talk to you about that, but talk to you about a spin-off. Because one of the things about doing deep science isn't about just saying, I'm going to think about things really deep and not explain to you what they mean, is realize suddenly you've invented a technology that might actually do something different. And what I want to tell you about tonight is this digitization technology for making chemistry available to all the chemists in the world, to make a chemistry that is similar to, I guess, the way you would view iTunes or Spotify, to make molecules of interest. Obviously, molecules that we need of interest are drug molecules to treat any disease, but really personalized molecules. And rather than talking about personal drugs, I'm going to talk to you about how chemistry might be digitized in the future, and why that there is about to be a digital revolution in chemistry that will make the digital revolution in Silicon Valley look like small change, because it will cure people, it will keep us alive for longer, and it will probably stop us from ending the world early because we don't have enough food or clean air. Now, these are pretty grand claims, but all I'm trying to do in my lab is 4 things, and I want to get money from as many different sources as possible to do those things. As a chemist, I want to make inorganic life form. I think that chemistry lacks big questions. There are many cosmologists here tonight, or people who like cosmology or astrophysics or observing the universe. And it's easy, if you're an astrophysicist, to say big things. Poor chemist has to make you, cure you, give you polymers and keep you, in a environmentally clean environment. And I'm happy to do that as a chemist, but I want more. I want to know why we exist at all. Why does life exist? So that's the #1 project we're doing in the lab. What we're also doing is, when we realized that we needed to build machinery to make life, I realized we had to digitize chemistry, and tonight is about that little kind of journey. The third thing that we're doing is, if I can use computers to control chemistry, to make the drugs you need on demand, can I use chemistry to do computation? Now, if you're confused for a second, I want you all to pick your favorite numerical equation and do it in your head. My kids will do easy ones, you might do harder ones, 1 + 1, whatever, it doesn't matter. But do that calculation, just do it for a second. Now marvel at the fact that your brain, full of molecules, has just done that calculation. Isn't that interesting that chemistry can compute? So this is something we're doing to compete with quantum computing, because your brain is far better than the quantum computer. We can discuss that in the social hour, not now. The final thing that I think is really interesting, that as humanity, we want to understand this transition to information. I will say one thing to provoke you, and then I'll get into my boring chemistry, I promise it won't be boring, my chemistry lecture, which is, a universe without life is a universe without information. The physicists are all wrong. Information does not exist outside of a conscious entity, because data exists, the universe exists, but I require, if I'm going to encode something, I need to decode it. So information requires encoding and decoding, an author and a reader. When you think in that way, and it requires a chemist to think in that way, suddenly you refactor how you see the world, which is kind of interesting. So I'm not trying to provoke you, but I'm definitely right. Information only exists where there is life. And I don't know what that means yet, and that's a new kind of idea that we're playing with at the moment, but I wanted to introduce it here, and I told Larry I'd be politely provocative. So, okay, so I'm a chemistry professor, and I need to make molecules to make a living, and there are lots of people giving me money, and I need to deliver stuff. What I've been trying to figure out is, making molecules is quite a difficult task. I don't know here, can anyone here is willing to put up their hand and tell me they remember doing chemistry as a student? Be it Scott, thank you. There's at least, so a few people did chemistry at high school, maybe at university and so on. Do you remember going into the lab and mixing stuff together and making fireworks and things? It's a very visceral experience. It's like being a Michelin star or not a very good chef. Right? You actually mix stuff together and it maybe works or doesn't work. That's fine. It's fine that your chemistry doesn't work. But when you buy an app to put in your phone, do you think it's okay if the app doesn't work? So this is an interesting question. And is there something special about the science of the program that works on your phone versus the program in the chemistry lab that stops the chemistry from working? First question I want to ask. But when you think about how computing works, if you look at all these different objects, computing has come a long way. This is my first computer, which I got when I was 8 or 9 years old, and then this one after that. And this technology has required a development of some abstractions that allowed us to build on a set of rules. And what I'm going to tell you tonight about is something's emerging from my lab, and I'm trying to convince chemists really rather, not begrudgingly, but they're all geniuses, right? Very stable geniuses. Come on, it's Friday night. Come on, live a little. And they don't want to be replicated, but at the same time, being able to take the things they can do and allow them to collaborate in the same way the digital technologies. I'm sure some of you here use program and take code from one another and build on that code, and that's one of the most fantastic things about the digital science revolution. So the first question I want to ask you tonight to think about is, wouldn't it be great if chemistry could adopt the digital science revolution? Wouldn't it be great if we could build on one another and make things reproducible, first of all, and safe, secondly, and then collaborate in a new way such that digital technologies have allowed us to do? Now, I'm not going to go into Facebook and Brexit and other phenomena. I'm talking about the good aspects that we get from digital technologies, right? The regulations we can talk about another day. To make that happen, we had to go from these type of transistors, these type of processors where the 8008 had 3,500 transistors. When I think I destroyed my mother's washing machine, was about 10. She had a Motorola 8080, had 4,500 transistors, which was enough for me to build a rudimentary computer. But rapidly through the years, they increased. And you can see that Moore's law has now got to the point where this is an iPhone, the latest one, because I could buy it, why not? Just to wind up my son. And it has 7 billion transistors. Who would have thought that 50 years ago you'd have 7 billion transistors on a handheld thing? Now, what I'm going to tell you about tonight is about the same thing that's about to happen for chemistry. In that the way that you think that molecules can be made is really hard and chemists are unreproducible. We're at the beginning down here. But we are going to establish a paradigm, or I'm going to tell you tonight uniquely about a paradigm that's going to go from here to here without failing. And what I'm trying to do is to try and challenge the chemists to access more molecules, because more molecules means more disease cure. More molecules means more chances of finding new materials that can room temperature superconduct. More molecules means that we can find more ways of making plastics that biodegrade on demand. You can go on, right? I'm trying to make a chemistry lecture sound really cool. You know, I haven't been into space. I'll tell you about the time I invited an astronaut to give a talk at one of my chemistry lectures. And it's all built upon this idea of universal computation. For the computers you take for granted to work, a number of important things needed to happen. First of all, someone had to describe on an abstraction and think in their head, the same way I asked you to do a calculation in your head, how do I abstract mathematics so it becomes computable? It's not that hard, right? We take it for granted now, but it was quite a transformation. So I would ask you to imagine that it's possible to do the same thing for chemistry, because chemistry is not magic. It's not. I'd love to tell you it was, and you needed to give me more money and more kudos, because I suddenly have this secret magical way of making drug cures, but it's not. It's based in physical reality. So what is it we need to do to get the abstraction that Turing managed to do? And Turing arguably invented the architecture for the digital computer. And of course, we revere him, but my favorite computer scientist of all time is actually John von Neumann. John von Neumann had a brain the size of the planet, as far as I can work out, and even bigger than Dick Feynman's, which is pretty large, because he was able to understand and abstract how machines built machines and then worked out the mathematics to make that happen. So von Neumann, with Turing together, developed an architecture that has given you our digital science today. And I mean, we can forgive them for Facebook and Twitter because they didn't foresee that. And actually, joking aside, if what we manage to do here works, we need to similarly think about the effects of if we can make any molecule we want, and I don't know how many grams of LSD you need to have to be told that you're in possession. I could just make a chemical computer to make me a few milligrams of LSD from legal things, and I'm never illegal. I'm still taking LSD. I'm not saying we should, but my point is that I'm not saying that we should violate our laws, but we should think about the impact of the negative consequences of them. So universal computing has been made possible by this idea that we have, first of all, a universal code. Now that we've got highly programmable, very simple, ubiquitous systems that can be programmed like Arduino, we can cloud everything, and then we can write code, and we can then instantiate it in a machine that will do your bidding. Who here has a 3D printer out of interest? Oh, there are at least 2 people. Awesome. I have a 3D printer too. Oh, 3. So, and I use it primarily to basically take mathematical topologies and print them and do AI. And I do physical encryption because I like to annoy mathematicians who think they understand AI. But that's another subject for another day. But I like 3D printing unprintable architectures. But the problem is that from a chemistry point of view, chemistry hasn't changed in 200 years. This bench, which is supposed to look like, Isaac Newton's maybe bench, maybe when he was playing around with mercury, or this beautified bench with my computer, or this microfluidic system, or this production line from a pharmaceutical factory, or this network of different chemicals that I would program together, and if I network them and they react at the right time, in the right space, they make something different. And for me, I liken this particular architecture to a fly-by-wire aeroplane. One of my favorite aircraft is a Typhoon fighter because the pilot can't actually fly it. There's someone here, I was talking about this earlier, it's like it falls out of the sky. You have to fool the pilot because the computer is updating the surface as 10,000 times a second. So they just point it, right? Right now, the chemist is like not the fly-by-wire. They are using the manual control of the chemistry, and they're only doing very gross things. If we can suddenly make the chemist a bit more fly-by-wire, what happens? We can control things and control synthesis in a completely different way. Before that, I'm going to give you some chemical reactions before we get going. There's an example here of a luminol reaction, which is a luminescent reaction with hydrogen peroxide. Basically works with luminol, and it gives you this really fluorescent process where you get photoluminescence, which is kind of fascinating. Another example here is a thing called crystallization, whereby we've got some material in a liquid and it starts to produce these beautiful crystals. They could be of a semiconductor you might use to diagnose something. They could be of a very important electronic material used to make a new solar cell to harvest light from the sun. But chemists use this kind of so-called black magic to produce the right combination of materials to make the outcome. You can see here, these are just dragged from YouTube. You can see this, okay, it's a bit boring to see, but you'll see in a moment this yellow solution is the crystals formed here. These materials forming in real time are the chemists manipulating the various chemical inputs. But the human beings doing that, much in the same way you might have to make a souffle and check that it's rising and not collapsing, or an omelette or whatever else, you have to interact with this in a certain way. Chemistry is about adding building blocks together. If you want to make that really important drug, you have to add building blocks together like Lego, using your chemistry kit, and in the end, you'll make a molecule that maybe you can use to treat all sorts of drugs. This here is Taxol. This is the most kind of important, or one of the most important anti-cancer drugs on the planet, but it's very difficult to make. In fact, it takes many, many thousands of hours to even make a milligram. However, if you had enough of this, you could probably cure any cancer that used vascularization. So because it starves the oxygen flow. But this molecule is in such demand, there's no way we can make it. It's actually a natural product gathered from a certain tree, and you'd have to, there's no way there's enough exists on planet Earth. So if we could make kilograms of this, we could cure a lot of cancer. But this molecule's really big. It's 70 steps. If you think about what 70 steps looks like for a chemist, it's like this. So bear with me. I know it's Friday night, it's tiring, and I'm giving you a chemistry lecture, and you all seem very engaged, so I'm happy. You do a reaction, or you do something, and you put in 100 grams, but you get out 50 grams. That's a 50% yield. Now you then take that 50 grams, you do it again, and you get out 25 grams. You can see, you put in the 25 grams, you get out 12.5 grams. You keep going. 70 steps, you're going to have nothing. 0. This is outrageous. Think about when the first transistor was built, or the first digital transistor was built, if you like, solid-state transistor by Bell Labs in 1953. I said there's about 10 billion transistors in here. In 1953, the Bell Labs transistor was about this big. If I strung those together to make anywhere near approaching a mobile phone, I would use the entire electricity output of the entire world for one device. So what I'm about to tell you is about a technology that's so powerful, I'll be able to synthesize your memories. And what do I mean? Well, you have memories in your head. Where do those memories come from? Do you think they're magic or they're molecules? They're molecules. But don't you think I could synthesize you new molecules, new memories? They're very big molecules, of course. They're proteins, they're sugars and whatever on there. I'm not saying I want to give you false memories, but let's just imagine I could synthesize you new memories. Or vaccines. None of this could be imagined in the same way that no one could imagine the revolution that would occur for having 10 billion transistors in a phone a little over 70 years ago. So this is what I'm telling you about tonight. The reason why this is so hard is that chemistry blue screens. Now, most of you probably remember what blue screening, well, there's some very young people who have like blue screen, everything works. Some of you my age or older will go, I remember trying to build my computer and it would just fail on me. And Windows would say, I'm sorry, I don't work. Here's my blue screen, here's the error. And this is what doing synthetic chemistry is like. A system error has occurred in your lab. This reaction is not reproducible. Synthesis of Taxol failed, it's step here, chemical dump, synthesis failed, 2 more months. Chemistry does not support universality, and this is not a joke. This is real. There are 200,000 chemists in the world today making molecules. These 200,000 chemists are the gateway to the new drugs, new discoveries, everything. But they can't even interact universally because they don't adhere to a common code. They don't have a common language. It's all kind of by the campfire, sing a song, remember it, go on. I know this is being streamed. I hope then not too many chemists. Oh, sorry, it's fiction. I would love it to be a real one, but yeah, I do have some computers in my lab that do dumps like this. I can tell you about that later. So why do we need more molecules? Well, chemical space is really large. We have basically searched far less than 0.00001%. In fact, far less. In fact, if you think about how big chemical space might be, I would tell you, if you take the Milky Way galaxy that we have now, we've just investigated, let's just say chemistry is like the Milky Way. We have not even got outside of our solar system. And that means we have no idea what molecules exist out of our solar system. We have only made, as chemists, 120 million molecules. Okay? But yet, there are over 10 to the 60 molecules possible. This is outrageous. I want my drug. I want new ideas. I don't want 120 million. That's a small number. And there's a very specific reason why we've failed in that task. Synthesis robots we've got are typically very expensive. They're not modular, they're not flexible, they're not connected. Chemical databases are very specific. Chemical discovery is time-consuming and yield-limiting, not universal. I can't promise to synthesize you your personal drug because I don't have enough manpower. It just doesn't happen. So how do we solve these problems? So a few years ago, my group, we decided that we would start to take cheap robotics, like 3D printers, where we could basically understand the XYZ coordinates and take pre-existing programs to try and turn code into molecules. And this lecture is about that grand aim. Could I write a program to make a drug and make it anywhere on demand when you need it? And would it be even better if I could take the program that needed your drugs on demand and make them anywhere when you needed it? So can we app chemistry? And the answer is yes, because chemistry is merely building blocks being added together in a sequence. So this is a really good place to start. So the vision is to take Taxol, turn it into code, and then once we've got the code to work in our lab, once I've done the hard work myself, the human being, I code it, and the robot can reproduce it. It's a bit like I've invented recording for music, if you know what I mean. In the days before we recorded music and even wrote music down, we would basically kind of go and listen to some music and perpetuate it. Chemistry is still in that zone. But we are needing to invent the microphone for chemistry and the tape recorder and tape player. And it may seem that I'm, making false analogies, but I can assure you that is not the case. If I can find a way to record in chemistry in my lab and play it in yours, suddenly we have access to molecules that we never had access before. And that is where we are right now, today. I could make molecules in my laboratory that no one else can reproduce because I don't have the right tape player. And what I'm telling you about today uniquely is a revolution that we've just come across that enables that playing to occur. We've also got a discovery system. Now, this is a really interesting picture of my laboratory now. Don't worry about this for a moment, unless you like doing chemistry. I did tell you this is a chemistry lecture on Friday night. It doesn't get hotter than this, I can tell you. So in this lab, in my lab here, this is a fume hood. A fume hood is basically a place where you can do the chemistry and the air gets sucked out and it basically keeps it safe and stops you from asphyxiating yourself or producing bad, noxious chemicals, and a human being can work. But we've got a number of different sensors. I don't know if anyone here has used a drone or a remote control vehicle of some description. This is really the same thing as you'd use in a drone. There is an altitude detection system, a GPS detection system, heat detection system. That's all these are. So this thing here, this NMR, this nuclear magnetic resonance, tells me how complex my molecule is. This mass spectrometer tells me how heavy my molecule is. And this infrared tells me how interesting the molecule is. The more interesting the molecule is, the more bands it has, okay? And that's all it does. So what I do is I randomly mix chemicals together and I look how new, how heavy, and how interesting. And that's it. So when we were able to do this, we basically went through chemical space and said, okay, how novel is the chemistry? Now, I don't know if you guys know what the definition of novelty is for chemistry. Probably not. Or definition of novelty if you're going to an art exhibit and you're looking at some modern art. What is novelty? I don't want to know the answer. We'll have a zillion different answers. But roughly, novelty is something that I like, but I've not seen before. Roughly. I guess you'd buy that. And so in chemistry, novelty is simply about if I can, oops, we'll go back. It works. So basically, if something I make is not predictable, okay, and but is new, it's novel. If it's new, but it's predictable, then it's just new. So if you're going to read someone's tweet tomorrow, who might be the president of your country, and you could predict the intonation of the tweet, that's not novel. If he or she, let's say, if you went and said, I am completely wrong, I'm so sorry this happened, I am now going to make amends, that would be novel, because that would not be predicted using the prior data. There you go. I've taught you something cool chemistry, right? But it took me, and I'm not making fun. It's like novelty is not about it's about the unpredictability of what you do. And so that's what we're trying to do in chemistry. And so this video here is to talk to you about novelty. But you can ignore it and imagine who has been to York in the UK? Anyone? Okay, only one person. Two? Or Edinburgh? Come on. Few more. Okay, right. I'm in Edinburgh and I need to drink. What do I do with my novelty algorithm? I do the following. This is a very interesting thing of finding new bars in Edinburgh. Is I would give myself a random orientation, so I rotate, I'll stop, and say I've got 500 steps, and I walk 500 steps. I promise I won't go too far in that direction because Larry, the video. Walk 500 steps, and I say, okay. I then stop, and I randomize, and I look and say, can I see a bar? If I can't see a bar, I just do 500 steps again. If I can see a bar, I say, great. I'm going to now reduce the number of steps I can move from 500 to 250. I half it. I still randomize, and then get my algorithm, I go search. I stop. I look. Can I see a bar? And if I can, no matter in my orientation, I drop my 250 again by half. And I walk, and I'll end up in the door of the bar. And we've found that this approach works for new molecules. 3 changes when you change your search radius from a random point allows you to discover new things. Now, it may seem a bit odd, but I would challenge you to go do it in Edinburgh or York, or anywhere, right? Maybe for museums in Washington or something, if they were open. Okay. So what we're trying to do in the lab is search for new processes for chemical space, that we're not worried about what the molecules look like. We want to know what they do, the observations in process space. Do they cure cancer? Do they superconduct? Are they blue? Right? So that's the first thing you do. Then what you do is you say, well, what is the abstraction of this property? Okay, and you take that out, and you then basically then do the chemistry. You work out what actual chemistry is going on, and then at the bottom you then work out how the chemistry gave rise to it. So it's really like it turns it on its head. Rather than me trying to build my machine using transistors, I basically randomly assemble a molecule and go, does it cure cancer? That's all we care about, right? I don't care about what the molecule looks like. Well, the patient doesn't care what the molecule looks like. The chemist does. And I'm saying to the chemist, no, don't worry about what it looks like. Does it cure cancer? Or is it blue? Or whatever it is you want. And then you go back and you change the way you search in that way. And that's one of the things we've been doing. So I'm going to give you one example of a discovery made in organic chemical space using this machine, right? This is a molecule here. If you're not familiar with the language of organic chemistry, this is going to look like just hieroglyphics. But basically, these molecules here, we added together to make this really strange molecule here. But this molecule, the only thing I want to tell you is this molecule was not discovered by a human being. It was discovered by an AI that was just looking for the new property. And what is interesting about this structure here, this was not invented by a human being. It was invented by the algorithm. And this is the first molecule to be invented by an algorithm. We published it earlier last year in Nature. And it's interesting because it could not be invented by a human. Because it was, just one of those arbitrary things. So how do we digitize chemistry? Well, we need to take software, a robot, and some chemistry. Because we need to control the way we will do the chemistry. Now, the wonderful thing about this is you don't really need to understand the chemistry in detail, and nor do I. It's like making an omelette. You don't need to understand the molecules that make the omelette. You know, if you crack some eggs, get some material, stir it up in a particular way, you'll get something that resembles an omelette. Then you'll then test what that omelette does. And I use this analogy a lot because in the UK we're trying to unscramble the omelette that's called Brexit and go backwards to let's leave that. And so if you now have the code, again, you don't need to know any chemistry. You just need to know the code. 3 eggs, 3 peppers, some ham, some cheese, order, and you write them down and say, do this, do this, do this. You now have a code to make the omelette. Chemistry is not that hard. All you need to know is the order of adding the chemicals together and know how to make an omelette, and you've made your drug. All the chemists that tell you that it's hard and you have to have all these hieroglyphics are wrong. They are telling you something different. They're telling you about understanding how we might draw other molecules later. It's not that they're telling you a lie, it's they're misunderstanding how it is we make molecules. So what we're trying to do in our lab, and if you bear with me, I'm not trying to be boring, I'm trying to be precise. I want to make a computer program that does chemistry. And I'm going to show you in the coming slides how that's going to work physically, really, practically. Now, if you think about this, this robot here solves a Rubik's Cube. You can see here kind of pretty well. Look, it does at the end. And I was inspired by this a few years ago and say, well, can I make a chemistry set that would basically, a bit like a Rubik's Cube, to do encryption? So you have a single write pad, and you might basically write down a special code and give it to someone. They burn it. Could I encrypt information using chemical reactions using a Rubik's Cube? And my research group went, well, okay. This is the kind of way we would do it. We'd have a 3D printer that would basically print a test tube, and you've got two different manifolds in the test tube, one that would allow this amount of yellow stuff and this amount of blue stuff. And you can see here, look, there's more. The volume down here is smaller. So this is a large volume, this is a small volume, large, small. And because we allow different volumes, we would make different chemicals, and we would have a way of encrypting our message by the volume of the chemicals, by allowing them to react. Very esoteric, but very interesting for me to develop the science of digitization. And then in the end, well, I told my group to 3D print a Rubik's Cube, and they said, no. But I said, well, I want to rotate. Because you imagine, I want to put some chemicals in device and rotate, like someone trying to crack a safe. And they came up with an L shape. This was the idea. Rotate by 90 degrees, and we can make these molecules. And that was the idea here with this chemistry. You could do the first reaction here, then rotate, do another, and do another. So by rotating your device, you can make different molecules. Don't worry about what the molecules look like. It doesn't even matter. So the fact that you rotate them in the clockwise or anti-clockwise, you get different molecules out. So what we worked out is that we can combine 3D printing and chemical synthesis. So why is that important? Those of you that know about 3D printing know that you can download, or you can get a code, you can download a program from the internet and put it into your 3D printer, it would make it. Now you got the idea that you could download the prescription to make the molecule, and you could make it. And that was when we started realizing we could start to fabricate our drugs that we needed in our houses, probably not to the FDA standard, so don't get too excited. But you could start to do chemistry locally that you couldn't imagine before. So we started to build 3D printers. This is the first 3D printer that does digital chemistry. It's a bit like, I guess, the Bell Labs transistor. And this makes ibuprofen. I think ibuprofen in the US is still ibuprofen. Yeah, awesome. Because I was like, is it Tylenol? I was like, no, it's not Tylenol. It's ibuprofen. And this machine here, this is just a 3D printer, a normal one, that 3D prints the vessel. And then these pumps here inject in the reagents, the chemicals, according to this process control software. But what's more important here is the first ever chemical code for molecule. And those of you that like programming, you open up a COM port, the isobutyl benzene port, the propanonic acid port. So these ports you're opening up on your computer are putting chemicals together, and they're doing chemistry. They're making omelets. It's great for the non-chemist, because you can make your molecules on demand. For the chemist, we're feeling like we're out of a job. A bit like, the Uber drivers looking at the Waymos. Is it Waymo? In Arizona, but they keep killing people, so don't worry about that. Yeah, exactly. So there's the first ever instance of genuine chemical code we published a few years ago. And because the referees were trying to publish it were so against it, we couldn't publish it anywhere. We had to put it in an open access journal that everyone said, oh, it's got such a low impact. I was like, well, okay. I mean, I don't really care about impact in a vanity sense. I need people to read it. And a lot of people read this journal. And so we managed to get it out there, and people would start challenging how they thought about chemistry and cooking. It's like, if you could reproduce the way to make a souffle or an omelette, could you reproduce the way to make a anti-cancer drug? There's only like 1 milligram on the planet, and if you don't have it, you're going to die. I mean, this is pretty serious, right? So then we said, okay, we should think of it about like an espresso machine, or you have, I don't know if it's spelled correctly. So this is one of the things we're developing right now, and DARPA have given me a significant amount of money to develop pods to make chemicals. And the idea would be, you have your machine, you put in the pod, you say what I want, and out comes a chemical on demand when you need it. Can we make that work? The answer is yes. And I'm going to spend 10 minutes telling you how it works. and the next 10 minutes extending that to all of chemistry. So the idea is like you view your chemistry like the omelette, the A, B, C, and D. You have them in there, you put them in the right way, and you purify them. And you can just put your little tab or your little capsule into your Nespresso machine. No George Clooney, I'm afraid, but maybe me getting there. And I still have my hair, come on. And you press the button and out comes the chemical. That's the idea. And so the reason why this is important is that if you kind of understand how single devices work, this here is a machine that produces music. According to these divots here, it's a music box. It only plays one tune. But every time you wind that, it plays the same tune. So I wanted to make a chemical drug fabricator that every time you put in the reagents, you wound the thing mechanically, you'd get the same drug out, irrespective of technology. And this is what we invented a few years ago to basically have zero capex, delocalize the logistics, go for unstable molecules, and can be cheaper off the shelf synthesis. Think about it right now. A lot of the drugs that you take, if you're taking drugs and you need them, are linked to one particular manufacturing facility with a particular patent. When that patent expires, the drug company moves you on to the more expensive one. You may not necessarily need that. How do we retain that information so it has zero cost to reinstate? This is what this does. So the idea is to do this for chemistry, that we can basically turn the handle and reproduce any drug that you need that's ever been validated by the FDA on demand forever. The upside is that you can basically then give drugs to the lowest billion in the world who have no access to materials. And then the upside is you can customize drugs for the billion that want to afford to kind of play around with their individual needs. I'm not talking to you about the morality of access and cost. I'm saying, can we just get drugs to everyone that needs them? I think it's really a humanitarian scandal that 2/3 of the world's population do not have access to the medicine they need. And there's no problem to give them access. That is one of the reasons why I'm here tonight. Not just to tell you about what a rubbish chemist I am, I'm pretty bad, but also how digitization of chemistry might enable us to change the world. Now, let's talk about the way we do it. So if you understand how computer automated design works, I'll design a car, design a new type of mobile phone to make it look cool, foldable, whatever. This is exactly what we do for chemistry now. So we can basically take the pipes and the tubes that you'd have in the chemical massive factory, but miniaturize them. And we would basically take the various chambers we need and we code them using standard CADs. And this is what we did. And this is a 3D printing architecture. Now, if you need a chemical, I just send you the CAD file. And I send you the IKEA kit. Anyone here have IKEA furniture? This is how easy it is. Because you follow the instructions and you have your chair. Or tool, whatever it's called. And we have made a series of devices that will make it so easy for you to reproduce quite complex molecules with no chemical understanding. You don't have to be a carpenter to be IKEA. You've outsourced that to IKEA. Why would you? So you want to get the flat pack home, unassemble it, boom, boom, there you go. Okay, you're like me, you don't read the instructions. It's a disaster. So this is how we have the molecular design. We basically use all sorts of open script. But let me just show you how it works. You have a kind of like a CAD for chemistry, a kind of brain which would be rule-based, where you set up the protocols, and then the process kind of allows you to do the chemistry. But let me show you it easier. So this is a video of one of my students basically making some reactionware using this simple device without knowing any chemistry. Now, if you look, they're choosing a device, a cylinder. Well, hey, a cylinder. And then they're basically going to take their chemistry knowledge and they're going to import it into the drawing. So they no longer have to know how to draw the motor car. You know, when the CAD designers are sleekly making their Lamborghini or whatever it is, I don't know what the equivalent in Corvette or something, I don't know. But anyway, I'm not American. Very cool. And you can then define all the different parameters from the chemistry. And what it does is it makes a 3D printed Nespresso capsule to make the molecule you want. And I think that's kind of cool. This video is 6 minutes, so I'm not going to maybe stand here the whole time, but you can get an idea from how easy it is, the chemist interacting with it and just saying, okay, how many connections do I need between the devices, right? Where does the filter need to be? And you can see the X-ray file here showing chemistry occurs in here and here. But before today, you thought chemistry was in a beaker, in a test tube, connected, limited, but it doesn't have to be. The physical chemistry can occur in an environment you can digitally define. Similar to if you're an architect and you want to build a building that has a particular type of configuration, or you're an electrical engineer and you want to define a type of circuitry to process a signal in a certain way. And you can see here this architecture being built, and I'll show you that in a second. So, I'm in the UK, we're very poor, Glasgow compared to MIT, very poor. So MIT was funded by DARPA before I got funded by them. Millions and millions. Oh, I hope they're not watching. But they're pretty good, and they're doing all right, he says. And we're going to talk about this molecule called baclofen. That is really a nice, interesting molecule. This is a molecule here. Now, again, if you're not a chemist, don't worry about the structure. Worry about the numbers here. And there are 10 things you have to do. 10 engineering steps, 10 things you need to get right to make baclofen. 4 chemical steps, 10 things. And what we decided we were going to try and do is convert those 10 steps into a 3D printed code by doing all this kind of, let's take the chemistry, A to B to C to D, all the different process, evaporate, cool, separate, lots of boring stuff, right? Turn it then into the module design, go from the concept of making the molecule to the digital layer to the physical layer. What does it look like? This is the MIT solution. Cost them, I don't know, $3 million. Took them 3 years. Our solution is here, costs $3. Yeah, but theirs is a bit better in terms of the amount it can make. Ours can only make 70 milligrams, so I don't want to be, but thank you, I'll pay you later. But you can see that the problem is they have all these electronic components that, you need to do this thing, all these dependencies, but $3. And just the tubing on here that you have to just apply the human being does it. There's no electronics, just IKEA. Please inject chemical, wait for 2 minutes. If you do it the wrong way around, it will explode, right, and catch fire and all that. But like your IKEA chair, it doesn't work unless you obey the instructions. So I'm going to show you a quick video about how this actually works, right? This is one of the highlights of the evening because you'll actually get to see if the video works. First of all, the conceptual layer. This is now the monolith that we design, and we're going to unravel it so you can see it. And here's the chemistry going in. So the actual chemical going in. What happens to the chemistry? We add in these things, add in the solvents. They get moved from chamber to chamber, and the transformation gets built up in a Lego fashion. And then in the end, as you keep doing it, you then make the molecule that you need, the baclofen, the anti-seizure med, in a nice, pure crystalline form at the end. How does it work? This is the 3D printer printing it. This is the person putting in the filters. We finish the printing at the 3D printer. Then this is the device. We kind of tap it, a bit of kind of mechanical engineering, if you like. Yeah, get rid of the dirt. Then we do the chemistry. But the chemistry is now restricted. You can't do what you want. It's a bit like if you're using a programming language, you've got to do what you've told. You can't go off piste. This is not a black run, right? We need to make a drug, not a poison. This is highly sped up, but you get the point. This is on a hot plate stirrer. They're adding all the reagents. It's all sealed. It can be, we're doing it in a fume hood to be safe, but it can be done outside of the fume hood because it's all completely safe. They're just injecting the reagents in. You can almost imagine ordering it from Amazon, right? Getting the reagents. I'm serious. That's what we want to do in the end. Think about it if it's a radioactive trace that you need, or a mission critical kind of material that's decomposing. Or as when we've Brexited in the UK, we need insulin and stuff, right? I mean, and so they have to cool it down here. But you can see, we can go on. I'm going to take it right to the end. So at the end, just to show it really works, because when we published this in Science, I thought everyone would go crazy at us, and we just made it up. So we made a video and then showed exactly how it would all work at the end, and we're now drying the product. And what's really interesting, they get the product out. This is enough dose of an anti-seizure med to give one person for a day. So it doesn't look brilliant, but look at that. No pharmaceutical industry required. No $300 million factory. The cost to re-instance this is the polypropylene and the 3D printer. Now imagine we do this with every pharmaceutical that exists, and the FDA don't go crazy and sue my ass or whatever, and we can get buy-in. We can suddenly make redundant drugs or orphan drugs and bring them back into print. It's a bit like this concept of out-of-print books we used to have before e-readers. And you'd only do a finite print run. That's how the pharmaceutical industry works right now. We are fascinated by this. Now, this is one example of doing it. How do we go further? So this is like the printing press. It's a very poor picture of a printing press, actually, to e-books, and how we go from here to here. So now, in principle, we can take any pharmaceutical that exists and make the barrier to recreating that basically zero capex. And I think that's a very important place to start for humanity, particularly for humanity in the world where we don't have access to drugs. And we think it's okay that children in sub-Saharan Africa are dying because they don't have access to the pharmaceuticals they need, or if you're in somewhere where the logistics are really bad and Amazon hasn't got drones flying there yet, that you can't actually get the chemicals there in time. Or when I first sold this was actually to the, I gave a TED talk a number of years ago, and the director of, who's actually a Navy guy as well, Jim Shradoveris, I can't ever say his name properly, it was the Supreme Commander of NATO, came up to me and said, I want one of those on the battlefield. And I was like, what? And what he was kind of saying is like, look, if you can make any chemical on demand, basically I can have our WMD solutions on demand. I was like, okay, that's kind of cool. Well, the FDA won't be happy, but I suppose if the soldier is alive to sue you for not using an FDA-appropriated drug, okay, cool. You can deal with that. But the concept was quick response to disaster. So this could be influenza, it could be a virus, it could be a terrorist outbreak, it could be anything. But the idea you could then send the code via satellite somewhere, and they would then make the molecule on demand as a function of your demand is kind of interesting. So let's move on a bit from there. So how do we go from alchemy to what I'm going to call now Chemputing? We need to take it a step further. I've talked about 3D printing and doing stuff out of the lab. How do we make everything in the lab universal? How can we make every chemist like a computer programmer writing code that they can put on GitHub, okay, that any other program in the world can use? One of the problems we have is that the cost of drug discovery is going up and up and up, and the rate of decline over 10-year periods is going down. And this is not because chemistry is dying, it's because the molecules we are making are boring. Why are the molecules we are making boring? Well, it's about the ability I have to run 100 meters in 10 seconds. I don't have the ability to run 100 meters in 10. It's about how much effort I have to put in to get to an interesting molecule. And this is the problem. The chemists are really good at making molecules, but they lose yield. So we need to find a way to supercharge the chemists. We are not replacing them. We're just enabling them to make more complex molecules. I predicted we will be able to synthesize memories. Well, okay, that's probably an outrageous idea, but wouldn't it be great if we could just synthesize antibodies? Because they are molecules. We don't have to produce them in cell-based systems anymore. Molecules are molecules. So the idea is we have to understand that chemistry is 200 years old. Combichem and robotics has failed in the pharmaceutical industry. Well, now we have this universal digital vision. We have invented binary code for chemistry, and we're going to make a chemical internet. And this allows us to take many more steps than we could take before. Whereas the average molecule would stop here, we can just add on more bits because there's no human cost. We just automate it. And that's the beautiful thing about how we can increase the molecular complexity. So the route to universal chemistry requires that we exploit 200 years of chemistry, the 200,000 bench chemists on Earth today, and we need to make it modular, safe, and reproducible. And how do we do this? I don't know, this is probably lost on a lot of you, but I can promise you this is the biggest transformation in drug discovery that's going to have happened in a long while, in that we take the round bottom flask, the thing I have used all my life, and all these 200,000 chemists use right now, all their lives, and we're going to digitize them. So what we're going to do is we're going to make a peer-to-peer network of chemists. Now you remember, I don't know, you might remember before Spotify, what was there for music? You're my friend, exactly. We're going to not make the mistake of Napster. We're going to go straight to Spotify, but use the Napster model. We're going to rip chemistry into the digital sphere, but not illegally. How can we enable chemists to not basically commit copyright fraud? Well, chemists, what they do right now is they typically would make a molecule, they'd keep it secret, they'd publish it, and that molecule could never be made unless you have a certain level of expertise. I mean, how rubbish is that? Just imagine you bought my molecule, say, right, Lee, I'm going to buy your synthesis of your new drug molecule. I say, there you go. Here's my paper. Thank you very much. $300,000. You go, okay. And you can't make it. You'd ask for your money back. But chemistry doesn't care right now. This is how it works. Whereas if you were to buy an MP3 or to buy a copy of a piece of art, it would display on your screen faithfully. It wouldn't pixelate it and say, oh yeah, no, sorry, I'm not going to give you the real picture. That's not allowed. So this is one of the things we have to counter. Now, I ignore all of this stuff over here for the moment. As a chemist, I realized that there are only 4 things you need to do when you're making a molecule. You have to do a reaction. You then have to work it up, do some stuff to it, isolate it and purify it, and keep going around in loops. Now, if you can do that, you can then turn that into processes that you can then code. So these columns, don't worry about, because I'll show you how it's going to work. So we realized that we can make a programmable modular computer with this programming language we built, where we could go from the magic code that no one understands to machine code that you would like binary. And so that's what we tried about making. So first of all, we had to design hardware to do it. And here's the modular system we made in my lab last year, finally finalized it. And what we were able to do is take these magic words that the chemists use and put them through a natural language processor to develop a code to make a drug or do a reaction. So this is like the amount here, 250 mil. What is it? Round bottom flask. Charged. What does that mean? Magnesium grit, and then basically take all these words and turn them into a code universally. So we made a binary code for chemistry. And so this is how we go from synthesis description to the molecule. But all you need to know, I can basically go from a special coded description and make a molecule. So the same way in the plastic before, I would send you the 3D printer file and the IKEA file. Now I just send you software code. And because you have it in your lab, you just plug the software into your lab and press the go button and come back 2 days later and you have your molecule. You haven't had to do anything. It's all automatic. So the idea is that we then turn it, we make it cost less than $10,000, implements all of chemistry, all 200 years. We have a concept of what's called a computer shift register for moving chemicals around. We use graphed locations for on-the-fly routing. And we have it fault tolerant and hot swappable parts. What do I mean by that? Well, it's like if any of you have used RAID arrays, a redundant array of independent disks. This is what we've done in chemistry. We have a redundant array of independent reactors. If your reaction has a 50% chance of failing, don't have 1, have 2. Then you have a 100% chance of it getting. If you want 1 gram and you need to scale it up to 10 grams, have 10. It's about, people did not make bigger disks. People added more disks together. That's how the digital revolution worked. They found the most reliable minimum component. Here's our Chemputer. So this is the chemist. So this is the automatic chemist we've all been waiting for. So this is, first of all, it's doing its cleaning. So it first of all clean itself with solvents. All automatically, and then the first thing that would happen is that it would do a reaction. So down here, adding chemicals together and a reaction would occur. This is a cool bit. You'd see lots of color change and stuff. Then the really annoying bit after the reaction is you have to separate it and do all sorts of magic to get the molecule out you want. So you have to do a separation. This is the thing that chemists spend 90% of their time doing, day in, day out. It's very dangerous, it's very time consuming, and it can be very failure prone. And now it's fully automated to extract out the molecule you want. You can see the color changing from here to here, and the yellow stuff going down here, that's the molecule, the yellow stuff. Then the robot automatically would remove the liquid to make the material come out to produce the molecule. There you go, there's the solid. And then the final purification process would occur by adding another liquid. And if you look at this, is there a human being touching it? It's completely automated. Does this mean the chemist feels upset because they have no role? Would you want your children who are, or you guys doing chemistry, to be in a lab just being liquid monkeys? No, you want to be dreaming about new molecules. In the same way you don't want the computer scientist. When I had my ZX81, I had to type in all my programs by code because I didn't have a way of recording them. I'm happy to do it once. I'm not happy to do it twice. I'm not happy to do it 10 times. So what we've made a way is to take all of chemistry and make it reproducible after it's been done once. This is now the production of the molecule at the end after the filtration. And if you look carefully enough, you'll see the thing being presented at the end here. Right down here, and there you go, there's your solid. This drug is actually Viagra. It's because it's a hard problem. I needed to publish it in Science, right? Even I'm not immune to a little bit of sales. So what we've got here is these 3 molecules. They're coming out in Science, I think, next week, right? And sleep, sex, and seizures, right? All I put here is nitol. You probably read nitol. The human can make it in 20 grams, 68% yield. The machine made it 10% less, but not bad. But the machine time benefit was 24 times. That means the machine dropped the amount of time you had to use interacting with it by 24 times. Take Viagra, 18 times, and it made 8 grams. I mean, that's a good payload, right? Yeah, I have to stop. And this is anesthesia, rufinamide, and again, so it's all on a gram scale. It's not microdose. These are real drugs. The computer, I could give code to make. So anyone builds that computer in the lab according to my specification, a bit like if I have a mobile phone with the right coding, I just give them the code, they input the chemicals, no chemist required, golden mouse click, 3 days later, these 3 drugs. What we've shown here is, in principle, you can take any chemical that exists, that humanity has invented, and do this to it. So there is no limitation for known molecules. And I think that's really interesting. And also introduced a number of lines of code. Nitol required 506 lines of code, rufinamide 101, Viagra 432, number of operations, amount of time. There's another video here that just shows you it working, and I like using these videos because it just gives you, you've seen a bit of it, but this is actually now the real reactions occurring in order for making the chemistry. And I won't show it all to you because it's a bit boring. Exciting for me that it still works, right? But if you think about this, all of this here, all these operations would be normally done by hand, by a chemist, but they are now actually effectively outsourced to the robot. The chemist now spends their time designing more molecules. And I think the thing is, I've got a lot of resistance to this. The chemists think I'm trying to replace them, but actually there's so many new molecules to discover, so many diseases to cure, so many new things to make. This is actually going to lead to more chemists being in chemistry, not less, because they can get to more interesting molecules. This doesn't replace the chemist. It's just a test tube. A referee said to me, who's going to get the Nobel Prize? Because the robot does it all. Like, I'm hoping that the person who invented the robot might get the Nobel Prize. I was like saying to the person who made the test tube. But it's hard, right? Because there is a lot of resistance in some of the way it works. But I think you've got the general idea of how this goes. But for me, it's just fascinating to watch. And as I said to you, the reason why we dreamt up this machinery was not to make drugs. I'm using this machinery to crack the origin of life, to do random chemistry. But I needed to build this machinery to have an outcome for it. Because if I went to the NSF in the UK and said, please give me a few $1 million for the origin of life, and they're like, to automate chemistry, they'll be like, no, we don't care about that. We'll give CERN $5 billion to make the Higgs boson, and look at how boring the Higgs boson is, right? It's like, I know the Higgs boson exists. Look, watch again. I can't, I'll drop it, right? Gravity exists, okay? But chemists don't get to do that. Hey, you physicists know what I'm talking about, right? But the chemists have to really sing for their supper. And so anyway, we'll carry on. And I think the important thing about the outcomes of all of this, I guess, is that in the end, the medicine that we make, the drugs that we need, aren't going to be turned into code. And they're going to be turned into code that are bespoke for us, because suddenly there's going to be some feedback from the genomic information that we have and the tissue-based information we have. Right now, we're inventing, so, okay, I don't agree with the Donald on many things, okay? But the NIH tells me that the opiate crisis is a crisis, and it would be interesting to solve the problem of addiction, right? So let's just imagine we could make enough opiate candidates, and I'm not going to color the machine blue and put a hat on it and call it Heisenberg, although it's tempting, you know, crystal meth and all that stuff. You know, I did have a crystal meth robot. It was actually a crystal, not meth, but it was crystal and some other compound. And my group were like, we can't do this. We're just going to go to jail, even though it's making legal stuff. But suddenly, if we can start to generate a larger chemical space of interesting molecules that we can use to treat conventional disease, and they don't have the side effects such as addiction or just causing other adverse reactions, then surely that's something that we should be targeting. The limitation right now is not society's requirements, it's the chemists being able to make enough candidates. So the robotics that we are building will allow us to test enough of those. And we have to find out new ways of exploring the new chemicals in tissue-based models. The other problem we have right now is we have too many barriers from going from the molecule to the clinic because we have arbitrary barriers. We have now ways of predicting how molecules are going to behave. So we need to 3D print tissues because we can with stem cells. We can then make random molecules, if you like, and show them how they behave in the tissue. We can then do an optical readout, and we can do machine learning to basically guess the right representation of the molecule we need to make. So there's a really interesting set of things that are coming together that will enable us not only to make new molecules, but to treat what we call disease states, and also challenge the current paradigm. You need a checkpoint here, a checkpoint here, a checkpoint here. What I would like to know, if I ever, or when I get ill, when we all get ill, is what does the disease state look like? And what is the molecule I need to treat it or reverse the problem? And I think the chemistry has done a lot of that. There are lots of molecules you can get to treat disease, from malaria on, but the time for discovery is too slow. What I've shown you here is a way of speeding that up and potentially personalizing it. So imagine every one of you had a robot with your name written on it. It's not so big, right? If I go back to the previous, you have a look at the size. It's not such a big robot, right? It's the size of a fume hood. It's this big. And the problem is that we need to now convince the FDA and the regulatory environment that actually we need to find a way of developing the Lego blocks to make a molecule for you and for you and for you and for you and for you that is only regulated for you. And I don't know how to do that yet. But if we can find unmet clinical needs that we can address using this technology, then I think it will start to convince us that we can develop the code. Because now, the way we design microprocessors, we use virtual simulators because we know so much about electrical engineering. I can build any processor and know how it works by daisy chaining the transistors together. I won't bore you with the details. I just know how it's going to work. I know how to behave. Within 50 years of now, we'll know how that chemistry will behave. And the regulatory problem will be shifted in such a way that we know what molecules you can tolerate. We know what building blocks. We might make a privileged opiate skeleton that we know we can all take, and then, okay, you need the methyl, you need the ethyl, you need the butyl, Larry might need the futile. Sorry, that's my joke for the evening. So I'm going to start to finish here, I think. The idea is that we're going to use software apps for drug design and production in the future. We'll print. So print is kind of not just print, but basically physically produced, like you saw in the glassware system. Drugs on demand at the point of need. Imagine you now go to your pharmacist and say, I need this molecule, and say, oh, it's in short demand. Oh, I'll just make it. I'll just download the stuff from Amazon. Drone will drop it in. The fact that there's only a demand of one person in this population that needs it, no problem. Customization suddenly becomes easy because we have the code. In the same way that you can take any computer code and customize it according to your needs. We'll then also download the diagnostics, which is kind of interesting. The problem with antibiotics is not that the antibiotics are ineffective because there's something magic happening, it's because they're overused. You need to find out how to use them correctly. There's no problem with antibiotics. There's a problem with diagnostics relating to the use of the antibiotics in the right way. The other thing that we're facing is that we really need to basically produce them on the fly in response to a terrorist or other disease outbreak or other unforeseen disaster. It's much quicker to send communication than material. And the only way that Elon Musk is getting to Mars is if he takes my computer. Well, they still won't talk to me, which is a bit of a cheat. But now, what do I mean? Well, look, if I go to Mars and I get toothache, or I need to have if I've got appendicitis, how do I take all the possible analgesics? I don't. But what I do take is I take the minimum amount of chemicals I need to make as many of those analgesics. When I have the problem, I dial back to Earth or wherever, and I have the code, and I make the molecules on demand. If we're going to Mars. I doubt we're going to Mars. But if you want to go to Mars, that's fine. But I think then that the thing that I think is really going to happen is this idea that we're going to combine the ability to make our own personal medicine that combines our genetic profile. How many people here, just out of interest, just out of curiosity, have had their genes sequenced? Fully or 2,3andMe? Yeah, I'm 2,3andMe. I mean, my father's also on 2,3andMe. It was hilarious. I got an email saying, your father is on 2,3. It's like, yeah, okay, I know. I gave him the kit, but thanks. I don't know. I think we both had the data protection turned off and it was fine, but it was a bit weird. And so, but you have this wealth of genetic information out there. I know I'm a fast caffeine metabolizer. I know what my alcohol flush response is like. I know all these things. Can we use them to tailor the drugs we're going to make? So I think this is where the future is. We're going to basically get to the point where we can just download a drug and press print, or go to your pharmacist and say, please make it for me. This is what's wrong with me. And this was years ago. And I think I was talking to Larry about this earlier. It's one of my interesting qualities is that I tell people what I'm going to do. It sounds completely outrageous. This goes back to, I think, 2000 and, I don't know, quite a long time ago. And we actually done it. What we predicted we would do, we're actually going to do. The only barrier to implementing this is cultural and regulatory. And also, we need to make sure that we actually solve some problems rather than creating more problems. Because if by talking about opiate addiction, all we do is get a load of people buying 3D printers and creating drugs for themselves, so everyone's like has a personal crack den in there, that's not the desired outcome, right? So there is a discussion that we need to have. I'm the scientist making this happen, but do you want it to happen? And what are you willing to sacrifice to make it happen? And is addiction in the first world versus curing 1 billion people in the third world worth it? That's not for me to answer. That's for me to kind of make it possible and to be open and transparent enough about the problems so you and humanity as a whole can start to kind of think about the tension between, need and this the epidemic that's in the US and the number of children that die in India. because we don't give them medicine. And of course, I'm from Star Trek generation. I don't believe in countries. I want there to be no Brexit. I want there to be no wall. I want there just to be a Star Trekian society where we can make everything that we want on demand and make a molecular materials fabricator. Thank you very much.
That was just one idea. So we have time for a few questions. I'm being told that my mic is not on, but it is on. Can you hear me back there? Okay, so there's a procedure for microphones. We have these microphone foam covers with different colors. I think we have a red microphone and a green microphone and a blue microphone. So if you have a question, raise your hand and the microphone comes to you and I'll point. You can stand up, tell us your name, tell us if you're a member, and speak into the microphone. You have to hold it a little close to your mouth to be heard. So we'll start with the green microphone there. The microphone, when it comes to you, should be on.
Except that one.
Except that one. So maybe we'll start with a...
Hello? Do you hear me?
Yeah, it's okay.
All right.
Okay, got it?
All right, I'm Brian. I'm not a member of this. Actually, my first time at the society. So,
Speak into the mic.
yeah, thank you for welcoming. My name is Ryan. First time here. Maybe just a point of minutia. I'm just wondering how your robot raises errors and how long that might take if some of the physical steps in the process are rather lengthy.
So the way the robot raises errors right now is the human hand codes it, or used to, and we would have a video. And what we would do is we'd have the human would do it by hand. Then we'd do what's called a simulation. So the robot would simulate it without any real chemicals, a bit like a dry run. Then we'd have a breakpoint run where it would do it with all the individual steps, and then we'd daisy chain it together. And we use a webcam to video it. And what happens is if we see any discrepancy between what we think is going to happen, what we predict is going to happen, and what's actually happening, it just raises a flag. And right now, unless there's mechanical failure, we have a 100% success rate, which is really good. 100%. Unless there's mechanical failure. And oh, Jesus Christ, we have some mechanical failure. We have syringes breaking. We have things falling off. But I think that's a really interesting phenomena. And we are now getting statistics on those failures, a bit like how automobiles fail and your back end fails and your gearbox falls out and things like that. So it's a good question. And we're going to continue to add to this because we're going to try and make sure, I didn't say, my mission here isn't just to do this in my lab. We are giving this away. All of what you've seen has cost me $10 million over 10 years, pretty much. And we're giving the whole thing away to make sure that humanity can copy it in their labs. We're going to do an open version, a plus version, where we're not giving it away. And what we can do is we can use that to gather more statistics and make it more robust, because this makes the chemists safer. The number of chemists that die making molecules every year is not zero. And what's happening in the UK and the US is we're outsourcing that molecule mating to India and China, so the deaths occur in the other end of the world. And that makes me unhappy. So I want to reshore because I want to do a bit of manufacturing because Brexit is just terrible and, we're going to have to grow our own food and everything. I'm not joking, right, at this rate, but anyway. But also, the safety for the chemist worldwide is paramount. So it's a good point.
Red microphone.
Sure. Hi, Dr. Newton Campbell. I'm a member. I was wondering if you could speak a little bit more to some of the artificial intelligence and machine learning research that you guys have now that you've sort of gone through this initial process of digitizing it. What are you using to discover new features for chemicals, for instance?
Yeah, so that's a really important point. I didn't go into it because it's quite mathematically technical. I'm a much better mathematician than I am chemist. So I invented lots of machine learning algorithms when I was actually 10 years old, right? So I've been wanting to play out. The problem we see with AI right now is AI requires a training set. So if you want to discover, how do you train something to discover something if you don't have a training set? I solved the problem and made all the machine learners really annoyed because all they do is multidimensional analysis. Machine learning is not secret. It is multidimensional regression. Anyone who tells you anything different doesn't really get the maths. Now, what I want to do is step beyond machine learning and go to probabilistic reasoning, which is not multidimensional analysis. It requires a different step in the science. So there is a problem with the way we teach mathematics and machine learning, a problem with the way we teach discovery, and a problem with the way we actually prepare people for the hype that's associated with each step. So let me talk about two aspects of machine learning. I could play tic-tac-toe with you, and I'm sure we would both draw all the time because we're probably smart. Well, I mean, I would probably lose because I forget, but you'd beat me, or we'd draw. Then we play chess. I have no idea who's going to win. My son beats me at chess, actually. He's 10 years old, and the scoundrel waits until I'm really tired and says, "We're going to play chess, Dad." I'm like, "Yeah, okay, no problem." And he's like, "Watch it." He beats me because he pays attention to the moves. In chess, the problem is still hard, and actually so hard that you can't solve it rigorously. Then when you get to Go, the number of states available is large, but finite. I could know them. The problem that people don't understand with AI is you have to know all your states. In chemistry, I don't know all the molecules. And so this is a problem that hasn't correctly been considered. So what we do at the moment, and I never thought that Donald Rumsfeld ever said anything useful ever, but he did. And what he said was this: there are known knowns. That is to say, there are things we know. Honestly, I kid you not. This guy I thought was like Satan made everything up. But for machine learning, Donald Rumsfeld understood known knowns, tick. Known unknowns, and unknown unknowns. Right now in machine learning, we can only cope with known knowns and known unknowns. That is, if I add together two numbers, even though I haven't yet ever done it, I will know what the outcome is going to be. I'll say that again. I could take the largest number that's ever been added to another number and do it, and I would know it, but I don't know it yet. In chemistry, there are unknown unknowns, and how do you search for those in the AI? The AI fails. But what we have developed is a entirely new approach to AI, and this is my next project. Once I've made the origin of life, I hope to do it. I want to work out why consciousness and creativity work, and it's to do with those unknown unknowns. Your ability to actually have ideas and create things that don't exist in anyone else's head is associated with a number of configurations uniquely open to you. There are more configurations of your neural network in your brain than there are atoms in the universe. And we're yet coming to grips with that. So basically, AI is a metaphor for multidimensional analysis. And so I know the AI people keep having a go at me about this, but they're just wrong. My paper I published in Nature last year, Google hate because they say it's wrong because I discovered stuff. I'm like, oh shit, that was the entire idea. Google doesn't discover novelty. Google only tells you what you've put into Google. Whereas my system tells you what you don't know yet. So I would say the way I deal with it is I do boring AI, that is I predict stuff. I do slightly novel AI where I try and figure out what processes will use make molecules, but the thing that excites me, as you probably gather, I just spent the rest of is like finding those unknowns. And that's why I think we really, really should start to pay attention to AI and realize that it's not special. It's just a multi-dimensional analysis reduction. It's not magic. AI is not magic. It's quite boring, in fact. Did that answer your question? Thank you.
Questions? Raise your hand. Sorry. Blue microphone.
My name's Scott Matthews. I'm not currently a member. I have a rather practical question about the 3D printed reactor vessels that you're making. The vast majority of common 3D printers nowadays use only a very, very limited number of materials, ABS, PLA, polypropylene, those sorts of things. Those things have a very limited mechanical strength. They have very limited temperature ranges over which they can operate. If you had high pressure or a high temperature in your chemical reaction, they would melt or blow up or whatever. So Can you speak to advances in 3D technology and the impact that that will have on the type of thing that you're talking about?
Yeah.
And then one other quick question, which is, if you've got all this stuff on GitHub, the plans for the reactor vessels, as well as the code to build the molecules, those could just as easily be used for nefarious purposes as for good purposes.
Yeah.
What's to stop people from making ricin or Bacillus anthracis or some other thing?
Okay, the first part. So let me answer the first part. So you know what we use? The plastic we use for everything is polypropylene. Because in fact, you can do 95% of all the chemistry you need in polypropylene. It doesn't blow up, it doesn't catch fire, it doesn't react with solvents. You just choose the chemistry you need that's compatible with polypropylene, which is kind of cool. But yes, we're making PTFE-based stuff. To answer your second question, so yes, we're developing new materials, but actually, I'm so surprised that all the chemistry we showed there is polypropylene. We have to use British plumber-based polypropylene because the stuff we get from China has a bit too much ethylene in it and it leaks. So you have to use pristine polypropylene, which is not cut with any ethylene, that doesn't leak. So that's kind of cool. And it doesn't blow up because when it fails, it just blows a bubble. The nice thing about these things is they fail to safety. Now let's move on to a really important point you made, and I completely agree. You can download, though, any paper to make ricin or Novichok. Novichok in the UK, we got into big trouble because, the Russians have been basically stealing your elections, and well, here they've just been building, anyway, let's not go there. I kind of disagree. I think that what you're suggesting is that I should be the policeman for everybody that does bad chemistry in the world. And I'm saying, no, my job is to show how you can do chemistry and make it portable. And make it reproducible because taxpayers pay money. In the same way that any chemistry you can get out of the published literature right now, you can make anything you want if you're dedicated enough to do it. If you decide to make that molecule and it's illegal, you are breaking the law. Don't forget that. We have this really false idea about cybersecurity and that, someone can hack into your bank account somehow, but the fact that your bank's fault, but it's not. It's the person who's hacking into your bank's fault. That's illegal. It's not. I could go and smash down your front door and rob you. That's not your fault because your door was weak. It's because I smashed down your door. I did something that was illegal. I should go to jail. That's how our society works. So now, what I'm trying to gauge from you guys, let's apply that same kind of standard. Would you prefer I didn't do any new advances in chemistry, making it reproducible, so your taxpayer dollars actually worked in all the labs in the world out of fear of people reproducing what I did for bad purposes? Or should I instead rely on the government and the legal system to prosecute people that did bad things? What would you rather have? And I think that's a really important debate. I'm not qualified to do that. I do what the taxpayer pays me to do, and I feel comfortable with. So I don't feel that it's my problem. I can download the terrorist handbook from the internet, as can you, and you can make ricin tomorrow. You could go to a hardware store and you could make all sorts of explosives. You could get hydrogen peroxide, you could get nitrates, is fertilizer not allowed? So now what we've got to try and do is understand, how do we regulate? So a friend of mine has made the terrorist SciFinder, which is, how do you work out who is going to basically make tomatoes or avocados and who is buying the chemicals to make a nerve agent? And what you can actually do is you can mine, using good statistics and good information, the purchasing pattern of someone who's about to make something bad and say, no, please don't do that, we don't want to die, and someone who's just basically growing an avocado. I don't know the answer to your question. What I'm trying to say is, actually, it's not my job to be your moral compass. My job is to make sure that chemicals are reproducible. That if you give me money to make a new molecule, I do not obfuscate it and I don't hide it. I make sure that humanity can continue to reproduce it. Now, is that bad? I don't know. I'd love your feedback. Because in some way, you're paying me to not tell people what I'm doing. At the same time, you want me to cure disease so other people copy what I'm doing. Is it my job to regulate society? I don't think so. This is a really good conversation to have. What do you think?
one of the reasons that I bring that up is because we're currently having a debate in this country about guns being printed with 3D printers.
You know the Darwin Award. Yeah.
It's an exactly analogous question.
You know the Darwin Award though, right? Because a 3D print is a ridiculous way to make a gun. Because when they fire it, it'll just blow their head off because it falls apart. Look, I can make a gun out of a copper tube from a plumbing manufacturer, right? And so I'm going to get some. I mean, it's easy. I can make a bazooka. I was looking at the White House. I was running today thinking, I can make a bazooka. Maybe I should, you know where I'm going, right? But I haven't, because I'm a law-abiding citizen and I trust in society. So my job is to make our lives better and to make sure your taxpayer dollars are not lost. And it's my job to be transparent about it and to have these debates openly so you can say, no, as a taxpayer, I object to you facilitating people to make crystal meth in their basement. One of the things we're doing is just to follow is blockchaining, making chemical blockchains so we can actually trace what's going on, and I can physically encrypt. I live in Scotland, come to Scotland because we need your taxpayer, we need money, right, after Brexit. All the whiskey stills are supposed to be beaten in a particular way, right, for their flavor, right? So the whiskey still, particularly in, say, in Islay, is supposed to be encrypted by the number of dents in the still. I don't know if you've ever heard this kind of. What we try to do with a plastic reaction where it's physically encrypt the ability to make the molecule you want. And that's really cool. And I'm not going to talk much about it now because it's under quite a lot of protection. But it stops people from copying us who don't know the full details because they'll make a poison. And there's no way you want to make a poison. So I think one of the things I would say to you is don't worry too much. I'm not trying to say advocate responsibility and we should all go and 3D print our own drugs now. I thought about it, and I thought of a way of physically encrypting, not using prime number based, cipher, but physical encryption that would allow any of you wouldn't basically go and cook up your medicine from reagents from the pharmacist unless you knew that they were reagent grade, right? You didn't want to die. So I think there's a bit of that in there. So that is a very important discussion going forward. So I hope that helps.
It's not a completely novel problem,
No, exactly.
Recombinant DNA faces the same problem, and more recently, CRISPR and its use to modify the human genome and for other purposes also have engaged a debate of a similar ilk. And one of the things you find is that there's a tiered way of providing security. So for instance, for smallpox, we basically remove smallpox from the gene pool that could be accessed to clone. On the other hand, the sequence information from smallpox became available. And so we had a very similar problem with making a very bad pathogen using readily available techniques that could be done pretty much by high school students.
One final thing to say before we go to the next question is that it's really like an arms race. One of the things, the moral imperative, we need to do it. Now, I don't know if you buy this. We need to do it because if we don't do it openly, transparently, other people will keep it secret. And that's really important. If I can do it openly and transparently with taxpayer dollars in the UK or the US or Europe or wherever, and then flag it so we can then make countermeasures, we're ahead. As soon as we outlaw it, other people will do it, and we will not know what they're doing. And that is really the biggest reason why competition occurs. But we could discuss it later.
Blue microphone.
Hi, I'm Carl Merrill.
You can be next. No, go ahead.
Okay, I'm a member of the society. I just wondered if you could comment on a competitor that you have. It's been here on the planet for about 4 billion years, and it's capable of making things like antibiotics, and it's biodisposable, and it makes them fairly cheaply. We have to purify it. But how do you compare what you make versus something that a fungus can make?
Well, that's a very good point. I wouldn't say that they are directly competing. I would say the fungus uses quite a lot of biosynthetic pathways to generate molecules that we don't yet really understand how to make. So I would say they're compatible. Wouldn't it be great if we could basically literally distill out of a fungus particular bioblocks so we could then elaborate? So I wouldn't see it as just to dismiss them. Wouldn't it be great if we could take a really complex set of molecules from biology, distill them in a large quantity, and elaborate them in one of these systems to make them even more interesting? So I don't think it's a problem. What I think is interesting is that lots of people spend a lot of time using biotechnology, they say it's going to work, and it doesn't work. Chemistry is more reliable than biotechnology. And I can tell you why in a few seconds. It's because the reagent, so I have a lot of friends who work in water treatment in Scotland. And so they basically put bacteria into the water where treatment works, and it works beautifully, but then suddenly you get a catastrophic failure, and no one knows why, and no one knows when. They can't predict it. So having both opportunities available, both bottom-up hard chemistry and top-down biology, is kind of cool because it gives you a inbuilt resilience. And as the chemistry becomes competitive to the size of biology, why would you let biology spend all that effort? It's very inefficient. I would disagree if you say it was efficient. It's very inefficient in terms of dollar and compound and carbon atom to make these molecules.
I'm not sure. I mean, because you have companies in undeveloped countries like India and places like that, and they're making very complex antibiotics, and it's not cost. I mean, on a
very limited. Yeah. So I would agree in that they are making very special molecules that they can access in very special ways, but you can't customize them. So what we've got here is I think they don't compete. You've got very special molecules over here that look. There's no way you could make these molecules right now. You have to grow them. Right now, you can have absolute control. You can make them. I think there's going to be a convergence at some points when you make a decision. Say, wouldn't it be great if we can combine genetic engineering and the computer? And we say, right, we're going to customize to grow, customize to make. So I don't think they're competing. I like the question because I think it shows the two ends of the spectrum.
Somebody have a microphone? A red microphone. Question.
I'm Jim Griffin, and I'm a member. My interest is really in your opinion of the scope of the artificial intelligence problem.
Yeah.
Okay, is that better?
Yes.
The scope of the artificial intelligence problem. And one thing I would love to meet is somebody who could give me a credible estimate of the brain's capacity. So
okay.
let me just ask you a question.
Yeah.
You have chemistry. Suppose I ask you, have you ever considered 3D printing a biological living object? And if so, how much more complicated is that than making your machines?
Okay, so that's the next lecture I'm going to give here when Larry invites him back. So we've actually started a project where we are, I'm kind of confident. Okay, well, I'll tell you anyway. So we are physically making chemical computers. We are making chemical computers based on fibers, and we are trying to look at how we can make consciousness in chemistry in the end. Now, here's why. Your brain roughly has 1 trillion neurons. That's 10 to the 12 neurons. Each neuron has roughly 1,000 connections. So if you take 1 times 10 to the 12 to the power of 1,000, there are more possible connections in your brain than there are atoms in the universe. So the artificial intelligence problem is not a problem. There is no such thing as artificial intelligence. It doesn't exist. Anyone who tells you that a silicon chip is going to overtake the world doesn't understand the connectivity problem. In my phone, I have 10 billion transistors. That's 10 to the 10. There's nowhere near 10 to the 12 times to 1,000.
10 to the 9.
Yeah. So 10 to the 9 times, sorry. Thanks for the maths, Larry. I'll pay you later. To 1,000. It's impossible. So you can't actually do AI. The problem is that Elon Musk is a great engineer who can't count. Okay? Max Tegmark is a great scientist who wants money from the people to pay him for the end of the world. AIs don't do anything interesting. They only do what we program them to do. So that's what I'm saying. Now, wouldn't it be great if I want to understand what is it about reality that produces consciousness? And again, there's another lecture, but let's think about the causation. Origin of life, biology, and we have chemical cognition. Bacteria can respond to stimuli. At some point, we go to multicellularity, and then the ability for you and I to abstract the world gives us an advantage to survive in it. That's the onset of consciousness. It's a really interesting phenomena, and it lies in chemistry. Molecules think. Your brain is made of molecules, they think. And there is no way an electrical engineer is ever going to emulate what molecules do, ever. The only chance we have, in my humble opinion, which could be wrong, because I'm a chemist on a podium, is to make a physical brain and program it. And that's what we're doing in my lab right now. We are taking gels, brain gels we're calling them, and we're training them, and we're showing that our brain gels are much more flexible than normal AIs. And this is why the entire AI community are riling against me, because they say, oh, what you're making it, just making it up, it's not good Bayesian mathematics, blah, blah, blah. Mathematics does not exist. If I jumped on your head, if you're a mathematician, when I killed you, right, the mathematics would be gone. And it's really interesting that physical reality doesn't, I know, don't laugh, I mean, I don't mean it from a, like, let's kill all mathematicians. I mean that mathematics is a construct of our reality that we build. There's something deeper than mathematics in our intelligence. We don't know yet. So your question is beautiful, but I don't know the answer. But my feeling is the human brain is the most complex object that we know of in the universe. And we are going to be hard-pressed to beat that in any millennia I know. And that excites me a lot.
No. Wait for the discussion later, because there are more questions. We're running out of time. So, blue microphone.
All right. Well, hopefully this one will be a little shorter. So I think I understood mostly how the computer, the basics of that. The earlier part of the talk, though, when you were talking about the 3D printed containers,
yeah.
And I'm trying to figure out what variables are actually being customized for each type of drug. I would imagine, for example, the number of containers that are chained together,
yep.
that would vary.
Yep.
But what are the other parameters? Does the size matter at
yep.
all? Does the size of the connectors matter at
yep.
all? Things
all
like
of it.
that?
All of it.
What would they be, just in general?
So, that's a pretty hard question to answer. What we try and do in general is we take the chemistry in the lab that a chemist would do, and then we try and app it or copy it and put it into the 3D printed device to work out what volume. You'd have volume, temperature, you might have aperture size, you might have time. So if you're taking a certain amount of time to move a liquid down through a vessel, that you then work at that out, and you could then, they're all the constraints we have at the moment, but you could add in literally anything. You could put in little components to allow for the purification or halt the reaction, inhibitors. You could put in poisons, if you like, to stop the reaction from occurring until it got to a certain point where then the reaction occurred, which I was talking about, the physical encryption. You put in one person's poison is another person's, So there's lots of things like that we're working at. But really, the key thing is, if you can do it in the test tube, you can do it in the 3D printer. Do it in the test tube, get the parameters from the test tube to work, and then transplant them directly to the 3D printer. And really, it's not much more technical than that. And it sounds like you've got it.
Yeah, but some of what you're talking about are chemical steps versus the actual physical characteristics.
Exactly. There's process steps and there's chemical steps, and they're convoluted. Yeah, exactly. Good point.
Red microphone.
That's how I feel.
Yeah. I'm Bob Hershey. I'm a member. It's called personalized. To what extent will personalization help in matching what's particular to each person's genome and getting the drug effective?
I don't know yet. But all I do know is that the more information we get, and so we can, let's be honest about personal. Right now, when a drug company makes a molecule, the only way they might personalize it is in dosage. So it's a function of your body weight. But there might be specific things they can personalize as a function of your metabolism. So if you're a fast caffeine metabolizer, alcohol metabolizer, you can change things. So wouldn't it be interesting if we could basically identify the type of individual you are metabolically and give you a slightly different drug? So I think that's the first layer. So the first layer is dose. Second layer is metabolic training. The next thing is to say, well, actually, what is your liver good at? Because because your liver is the gateway to drug regulation. And if we can understand how your liver processes organic molecules, then you're going to have a different profile. And so that might be that you can basically accept a slightly larger dose of a particular type of molecule before having liver failure versus another. And I think that's what we're going to do. And I would advocate very strongly for combining tissue engineering and chemistry together, for having these intermediate steps of formulation and stuff. Bring them together. I want to know if I can cure the disease state in the tissue as a function of the chemistry I'm putting on that tissue immediately, rather than going through all these other intermediate committees. And that's what I was kind of getting at. So it's a nice point.
We're going to do 3 more questions. Green, then blue, then red. Green, blue, red.
Thanks. My name is Wes McDermott. I'm not a member, though I have applied. Another sort of technical question. It seems like for known molecules, this works really well, and that's great. And there's a pathway to making lots of interesting unknown molecules. But when you make unknown molecules and you want to find out more complex properties, like can it help create artificial life or cure cancer, then it needs to be clean. But every time you make a new molecule, you've got new contaminants and new properties. So do you have a strategy to deal with that?
I just finished writing a proposal to DARPA today, actually. The due date's on the 14th, that tackles part of that problem. But actually, it's a really good question. It's not such a big problem, because purifying stuff is actually okay, is easy. We can do it. Problem comes at basically making things going from automated to autonomous. So the plea I have is, if any of you have inspired or think that you would like to know more about any of this, and you want to solve a particular problem, you have to turn your problem into an assay. So what I mean by that is, let's say you want to, I don't know, cure a cancer state in a cell. You need to have that cell, and you need to have an assay for curing that. Or if I want to basically make a particular type of physical property, let's say I want to make a magnet, well, I need to have a magnetic assay. So it's more important than the byproduct having the correct detection for the new thing you want to build on it. And one of the things we've been trying to do, where this came from, is to use evolutionary processes to basically enrich our artificial chemical space, to use Darwinian evolution to make it better. You generate a load of mess. So I would say that actually you don't want it pure, you want a mess. Because you don't care about how the mess works, you just want a solution. Look at biology, it's messy. But yes, of course, if you're a single point chemist and you want a single point solution, you have to separate at some point. So that's there as well. So at the moment, we're playing with both of those outcomes, both of those. It's a very insightful question. You do need to remove the contaminants at some point, because there's no way the FDA can let you discover a new drug and put all the contaminants out there. But wouldn't it be interesting if we discovered a stuff that was a cure for something really important, but it needed 1,000 different components. And it was a bit like the fungus, say, you know, like let's say we're not a pure material from the fungus, but a whole ensemble. Right? And how do you deal with that? We haven't even got to the concept of using more than 4 or 5 drugs simultaneously to cure anything. Well, why should we? If I can cure, you know, pancreatic cancer with 1,000 different components, I'm not going to argue with you. I'll just say, please cure my pancreatic cancer. I won't want the FDA to validate every single one of them. So I think what we need to do is think conceptually about how we define a disease state in the assay, and how do we determine toxicity. And I think that these are unmet questions right now. So it's a good point.
Blue.
My name is Robert Thompson. I'm not a member. This is actually my first time here. Now I'm a physicist. Thank you. So I don't know anything about chemistry, but I'm interested in how you are exploring your chemical space. You described this sort of random walk, essentially. But the chemicals that you produced in your setup, the 3 different ones that you produced, they entailed a huge variety in the number of steps and processes and things. So is it that you are randomizing, you just dump a bunch of stuff in and then sort of randomize the processes that you undergo? Or is it more of this sort of directed evolutionary type of approach that you were just describing?
So in both actually, but to show that the three examples, we deterministically determined them to actually make them. So we should say, we took three drugs and said, how do we make them in the computer? Going to the discovery system, we just chose some chemicals, a bunch of chemicals, and search for new ring activity. But going forward, we have to take both those extremes. And what you can do is you can map the quite complex mathematically, but simple chemically. What you do is you just map the interactions into a particular space, and then you randomly select them. I like randomness a lot because it removes my bias and my priors. I then do random stuff, and then I update my database. And then I update my database according to the outcomes I measure. So I think there, again, that's the important thing that we have to be able to do better. It's not the most satisfactory answer to your question because we're not entirely at that point where we can control everything. But that's ultimately where we want to go. Right now, we have a system that can take the entire database and in principle, take all of chemistry that's known today and make it robotically. And that should work within 10 years. Like, in principle, there's no barrier, just money and people willing to uptake it. There's no new science. What requires new science is this probabilistic discovery and moving away from the rather naive notions of AI that we have right now. Because the problem is AI is contrived by big data people who basically know what they already have, like Google Maps looking at, or Google Earth, or whatever it is. There is a fundamental disconnect between discovery science and AI-driven science, which I think is very cool. AI doesn't discover anything unless you think really creatively about how you define your discovery. So there's a big gap.
Last question, red microphone.
Hi, my name is Kelly. I am not a member, but I attend regularly with a member. So I was really interested in your talk about the whole regulation and the FDA, because I feel like a large part of that is we do not know from a biochemistry standpoint or a medical standpoint fully what's happening in anybody's body. So I feel like to get to truly personalized medicine, we have to kind of test in a lab what will happen to that person. And at some point, we need to know quite a bit more about what is going on with that person. Do you expect that we would need to do a similar kind of revolution in the way that biochemistry happens, in the way that medicine happens, to get to a similar level of volume or understanding or discovery with the same kind of speed that you're talking about with chemistry?
Yeah, okay. So I think there's three really important points. It's a really good question. The problem with personalized medicine is that there's only one subject to test it on, and that's you. So there is a really important problem there, is that you're never going to get a statistically valid sample. So what do? This person's presenting with a disease that's unique to them, right? Because we're going to cure most other things, right, and go down. And then you say, right, well, how can I validate it's safe for you? There's a number of ways to do this. The first of all is what you do is you go into a subset of molecular space, of drug space, where you know that all the molecules in that space are safe for everyone because you basically tested all of them, if you like. You understand how that fragment works. It's a bit like testing how good a certain aerofoil is on an aeroplane or a car, right? And then you customize it slightly. So you know it's going to behave differently in each biochemistry. And that when it's unsafe, it's just going to do something that's not like life-threatening. It's just basically changing the pharmacokinetics or something. So there's a bit of that. The other thing is you could, if you want, I suppose, I don't know, let's imagine 100 years from now and everyone's born, you basically take some cells, stem cells, whatever, embryonic cells, and you keep them, and you might be able to then develop them. And wouldn't it be interesting if you could accelerate the production of cells from the embryo faster than the human being that develops and predict their disease state ahead of time? Now then what you do is you predict what diseases they're going to get 20 years from now, and you solve that problem ahead of time, and then you give them a drug. Now there's lots of ethical issues associated with that, of course, but I don't know how much else you would do it. Now, it might be that you don't need to do it from embryonic cells. You could do it just from stem cells associated with you when you were born. You know, I have two boys, 10 and 12, and we still have their milk teeth stashed away somewhere. And I was like, God, we should have taken some of the stem cells out of their teeth, right, and kept them. That might be a way to do it. I don't know. But wouldn't it be interesting if you could take some of your biochemistry, accelerate it, and work out what the most deleterious consequences are going to be and cure them before you even know you're going to get ill? I just made that up just now.
No.
But I think it's a good idea, nevertheless.
For the social hour to be discussed. In the meantime, before you go, let me give you a few tokens of thanks. First is a signed copy of the announcement of your talk.
Thank you.
Signed by members of the General Committee on behalf of the membership. And the second is a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington.
Thank you very much.
Thank you.
Thank you.
So before we adjourn to the social hour, there are a few closing items. PSW depends on members and sponsors, without which PSW would not offer these lectures for free. So if you're not a member, please consider joining. If you are a member and you haven't paid your dues, please pay your dues. And if you're a member who's paid your dues, please consider giving more, sponsoring a lecture, endowing PSW, or volunteering to help out and carry out the Society's activities. You can apply for membership on the PSW website. I'm going to see if this works for me. Whoops. Here we go. If you go to the home page, which is up here, there's a little button up in the right-hand corner. It says join. When you push that button, you'll pull up this page with a membership application form. And when you click on the membership application, guess what? You'll get an application for membership. It'll ask you to provide contact information and a bunch of other stuff. And when you fill it out and you've made sure to fill in all the required fields, you get down to the submit form button. And when you submit the form, it will ask you to pay your dues. The form will be sent to the members of the General Committee, and your membership application will be considered. And if you have an interest in science, you will be elected to membership, and you won't get your dues back in that case. In the unlikely case, and it is a very unlikely case, that you are not elected to membership, you'll get a refund. So don't worry about it. Also, don't be fooled by all the PayPal buttons. PayPal. Is it PayPal? Yeah, PayPal buttons. You can use a regular credit card. Just look for the little button that says pay by debit or credit card. Trust me, you do not have to use PayPal. It's just their way of trying to trap you. But you are smarter than that, and I know you can navigate this site. Our next speaker, I should mention, of course, that PSW is a nonprofit educational organization, tax exempt under Section 501c3 of the Internal Revenue Code. Contributions are tax deductible to the extent permitted by law and the Internal Revenue Service, which is probably closed now. All PSW members in good standing can wear the PSW rosette. If you wish to purchase one as a member, you may do so at the rosette table, back of the auditorium. So please see our rosette salesperson back there. Okay, if you have any questions about membership, please ask our membership director, Lloyd Mitchell, or our corresponding secretary, Robin Taylor, or our media director, Ann McQueen, or me, but preferably one of them. The next lecture will take place at 8 p.m. here in the Powell Auditorium on January 25th. The speaker will be Todd Coleman. Todd is a professor of bioengineering at the University of California, San Diego. He will be speaking on wearable biosensors, particularly for gastrointestinal disorders. The rest of the spring schedule has been posted to the website. For those of you who follow, I have one change. Unfortunately, on February 22nd, Davey Bach will not be able to give his lecture on neuromapping which would have been apropos for tonight's closing remarks. Hopefully we will have somebody else speaking on a similar subject, but keep checking the website. On February 8th, Raman Sundram of the University of Maryland will be talking on supersymmetry and multidimensional spacetimes in a lecture sponsored by PSW Frank Robert, who I think is in Australia. On March 8th, Ramesh Gopinath of IBM will be lecturing on blockchains in commerce. This is not going to be about cryptocurrency. For those of you who are interested in that, this is going to be about other uses of blockchain. On March 22, Jim Gavin and colleagues will be speaking about Venus and making the case for a return there with robotic explorers. On April 12th, Mary Angela Lasante of Princeton will be speaking on dark matter in a lecture sponsored by our own PSW member, Erica Kane. On April 26th, Kim Janda from the Scripps Research Institute will be giving what promises to be a particularly interesting lecture on making vaccines against drugs of abuse. On April 29th, we have a very special event, a debate between Alan Stern, the principal investigator on New Horizons that recently visited a Kuiper Belt object, and Ron Eckers, who is the former president of the International Astronomical Union. Their subject of debate, which hopefully will be a civil discussion, is what is the proper definition of a planet? And, of course, is Pluto one? As you can imagine, the man who promulgated and served as principal investigator of the robotic New Horizons explorer of Pluto will argue that Pluto should be a planet. And the man who was in charge of the committee that decided that Pluto was not a planet, Ron Eckers, will argue that, no, it's a dwarf planet. So it should be a lot of fun. It is a Monday night event. Keep that in mind. And then the spring schedule ends on May 17th for the 87th Joseph Henry Lecture, which this year will be given by Brian Keating. Some of you may know Brian for his recent book on losing the Nobel Prize, in which he takes on the idea of big prizes in science, but also has very interesting biographical account of his own research and how he went awry, trying too hard, too fast, too soon to publish, to win the prize. I'm hoping that he won't talk about that, though. I would like him to talk about inflation at the early time in the universe and at the beginning of time itself. So that lecture is sponsored by my own firm, Millen White, Solano, and Brannigan. And with that, I think I'll entertain, I have to tell you, the social hour, to which we will be adjourning shortly, ends at 10:30 or thereabouts. And after that, if you wish to continue discussion, we go across Massachusetts Avenue to the Fairfax Hotel Lounge in an event that is primarily for members of PSW. But if you are not a member of PSW and you have not attended the event more than once or twice, you're welcome to join us. If you would like to do so, please see Ann McQueen or Robin Taylor, and they will tell you how to get there. So with that, I will entertain a motion to adjourn the meeting. We have a motion. Do I have a second? All members in favor of adjourning to the social hour? All members opposed? Meeting is adjourned.